So we know about character tables now. That's some kind of stupid cookbook recipes that says, well, there is orthonormality and that puts constraints, and then you try this and that, and you get a character table. And here is an example of a simple table. Character tables are square because the number of classes equals the number of irreducible representations. So that's what they look like. They're not just some random tables, they're actually unitary matrices. And what they do is they're changes of coordinates from basis, vectors and coordinates, which are based on your group elements, a different basis, which is called irreducible basis in general. It's called momentum or frequency space in case of Fourier transforms, but this is a generalization of those. When we work through Fourier transforms, you'll see literally, this stuff. Now it looks a little bit weird. To understand that they're unitary, I told you, well, you can put all these characters in a matrix. A matrix that corresponds to a table has rows in which you look at given irreducible representation and you enter a character for each class. So that's what the rows are. And when you look at the columns, what you do is you keep class and enter the entry for every class. And then there was this awkward thing. It says, well, I can rearrange them in such a way that I turn rows into columns. So yellow column into yellow row. And then I count how many elements I have in a given class. And yeah, it's another matrix you can write, but we got the second orthogonality relationship from it. I just want to make it very clear that these are unitary transformations. In practice, one doesn't do it the way I'll do it right now, because I will rescale all the elements with square roots of something. And when you write character tables, this way that's done in Dresselhaus and all the chemistry textbooks is right, because you get some very simple integers quite often. So that's why people like it. And same thing happens with Fourier transforms. People like to write them in asymmetric ways. So let me define a little bit notation. So let me say that whenever I take any set and put vertical bars on its side, by that I mean this is a cardinality of the set, or number of items in the set. For example, when I write capital G, meaning I have a group like D3 or D4 or dihedral group or some other group, when I put it into vertical brackets, the number that I mean by this is what Dresselhaus textbooks call H, the number of elements in a group or order of the group. And if I take a class, that's a bunch of group elements, their number that Dresselhaus call NK, I'll call bars around the class. So then I'll look at these two definitions. Let me take character and this horrible notation that, up there is a thing, and if you do it in Dresselhaus book, it's called capital gamma I. But I'll just call Greek character alpha. That labels the irreducible representation. And you have to compute that character on your class, because it's same for any element in the class. And then I'll multiply it by square root of the ratio of these two integers. And if I do that, the left-hand side, I can just write it as a matrix chi, where the row of the matrix is I run over the classes for a given irreducible representation, and the column, I fix the class and I run over irreducible representations. So that's just compact notation for this, but I've rescaled it by a square root, which I've distributed. Now, when I do that, the other guy turns out to be simply transpose complex conjugate of what's called Q prime here. And now what's happened is that what for chi used to be a row, after transposition becomes a column, but complex conjugate of every character. And what used to be a column now becomes a row. And in this balanced notation, chi is just a unitary rotation. And what chi does, it sends, if I had a vector of classes and I multiplied it, it would send it in the reducible representations. So when I act on a state that's labeled by group elements divided in classes, that will produce, this thing will produce irreducible representation. And what chi prime does, it just goes back, and it's a unitary matrix because, if I multiply these two guys, with all our orthogonality relationships said that the product of these two matrices is one identity. So that's how you have to think about all this voodoo about character tables. What's going on is, we proved a miraculous thing, which is totally not obvious, that whenever you have a group representation, that group representation can be brought to unitary form, where all the matrices are unitary. This doesn't happen in real life. If I give you some, matrix and you try to diagonalize it, you will not find in general that this matrix has strictly positive eigenvalues. That's what we proved, because we could bring it to diagonal form and we could take a square root. That's miraculous. If you Google and go to Wikipedia, if you take a symmetric matrix or Mission matrix, you will find out that in general, eigenvalues can be anything. Or for Mission matrix, they're real, but they can be positive or negative or zero. But the group property of these matrices enforce that they are all non-vanishings because group must have an inverse. So representation must allow for inverting these matrices. And they're all positive. That's a big deal. So that's what I think you should take about character table. They're just the unitary representations from your coordinates where you had 3 balls and you permuted them, and that looked natural to you, to irreducible representations, so much smaller matrices than 6 by 6 or factorial time factorial matrix, in which the blocks were separate and irreducible, and there were atoms of any possible representation. So that's what we learned so far.